Tonight, we're going to talk about something that broke the way I think about size in the universe. We all grow up learning that galaxies are the largest visible structures out there. Hundreds of billions of stars bound together across 100,000 light years. That's the big thing, right? That's the ceiling. But there is an object sitting at the heart of a distant galaxy cluster that has produced a structure so enormous it makes entire galaxies look like specks floating inside it. It wasn't built by gravity slowly gathering stars over billions of years. It was inflated by energy, raw, violent energy pouring out of a single point at the center of one galaxy. And when you understand how large this structure actually is, galaxies stop feeling like the biggest thing in the room. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with what most people think of as the biggest visible things in the universe: galaxies. And that makes sense. A galaxy is an enormous collection of stars, gas, dust, and dark matter, all bound together by gravity into a single massive structure. Our own galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars spread across roughly 100,000 light years. If you could somehow travel at the speed of light, the fastest speed possible in the universe, it would take you 100,000 years just to cross from one side of the Milky Way to the other. That's an almost incomprehensible distance. The entire history of human civilization, every empire that rose and fell, every invention, every war, every moment of peace, all of it fits within about 10,000 years. You would need to repeat all of recorded human history 10 times over, end to end, just to match the time light needs to cross our galaxy. So galaxies feel like the natural ceiling. They feel like the biggest thing you can point to in the sky and say, that is one object, one structure, one gravitationally bound system. And for a long time in the history of astronomy, that intuition guided how people thought about the cosmos. Individual galaxies floating in the void, separated by millions of light years of dark, cold, empty space. But here's the thing most people never learn. Galaxies are not the ceiling. They're not even close. Because galaxies don't exist in isolation. They cluster together. Gravity, the same force that holds you to the surface of the Earth and keeps the Earth in orbit around the Sun, operates on every scale in the universe. It pulls dust together into planets. It pulls gas together into stars. It pulls stars together into galaxies. And then it pulls galaxies together into groups, and those groups into clusters. A galaxy cluster is exactly what it sounds like. It's a massive collection of galaxies, sometimes dozens, sometimes hundreds, sometimes thousands of them, all gravitationally bound into a single enormous structure. These clusters are among the largest gravitationally bound objects in the entire cosmos. Nothing bigger than a galaxy cluster is truly held together by gravity. Superclusters and cosmic filaments exist on even larger scales, but those structures are being pulled apart by the expansion of the universe. Galaxy clusters, though, are dense enough and massive enough that gravity wins. They hold together. They persist. They are real, coherent objects. Our own Milky Way belongs to a relatively modest collection of about 50 galaxies called the Local Group. The Milky Way and Andromeda are the two dominant members, and the rest are mostly small dwarf galaxies orbiting around them or drifting between them. The Local Group spans about 10 million light years across, which sounds enormous, and it is enormous by any human measure. But by the standards of galaxy clusters, the local group is tiny. It's barely a group at all. The Virgo cluster, for example, sits about 54 million light-years away from us and contains somewhere between 1,200 and 2,000 galaxies. Some of those galaxies are far larger than the Milky Way. M87, the giant elliptical galaxy at the heart of the Virgo cluster, contains roughly 1 trillion stars and harbors a supermassive black hole with a mass of about 6.5 billion times the mass of our Sun. M87 alone dwarfs most galaxies in existence. The Virgo cluster, taken as a whole, is an impressive structure, but even the Virgo cluster is not what we're here to talk about tonight, because there are galaxy clusters out there that are far more massive, far more energetic, and far more extreme than anything in our cosmic neighborhood. And one of them, sitting roughly 5.7 billion light years from Earth, is one of the most extraordinary objects astronomers have ever found. It's called the Phoenix Cluster. The Phoenix Cluster was identified using the South Pole Telescope, a specialized radio telescope located at the geographic South Pole in Antarctica. The South Pole is one of the best places on Earth for certain types of astronomical observation. The atmosphere there is thin, extraordinarily dry, and remarkably stable, which makes it ideal for detecting the faint signals that distant galaxy clusters produce. The Phoenix Cluster was found through something called the Sun-Yayev-Zeldovich effect. This is a subtle distortion that hot gas inside galaxy clusters creates in the cosmic microwave background, the faint glow of radiation left over from the Big Bang that fills the entire sky. When photons from the cosmic microwave background pass through the hot gas inside a galaxy cluster, they gain a tiny amount of energy from interacting with the high-energy electrons in that gas. This shifts their frequency slightly. The photons come out slightly bluer, slightly more energetic than they went in, leaving a measurable imprint on the background radiation. By mapping these tiny frequency shifts across the sky, astronomers can detect massive galaxy clusters even when they're billions of light years away. It's a brilliant technique, and it's how the Phoenix Cluster first revealed itself. When astronomers identified this cluster and began studying it in detail using X-ray telescopes like NASA's Chandra X-ray Observatory and ground-based optical telescopes, they realized they had found something genuinely exceptional. Not just another massive cluster, but one of the most extreme environments in the known universe. The Phoenix Cluster is one of the most massive galaxy clusters in the entire observable universe. Its total mass, including all the galaxies, all the gas, and all the dark matter holding it together, is estimated at roughly 2.5 quadrillion times the mass of our Sun. Let me try to put that number in context because figures this large tend to slide past without registering. 2.5 quadrillion solar masses. That's a 2.5 followed by 15 zeros. The Milky Way, which already contains hundreds of billions of stars and seems unimaginably large from our perspective, standing on the surface of a small rocky planet, has a total mass of about 1.5 trillion solar masses when you include the enormous halo of dark matter that surrounds it. The Phoenix Cluster is roughly 1,600 times more massive than the entire Milky Way. Everything our galaxy contains, every star, every planet, every moon, every asteroid, every comet, every cloud of gas, every grain of interstellar dust, all of it combined, is a rounding error compared to the mass of the Phoenix Cluster. If you took the Milky Way and dropped it into the Phoenix Cluster, it would be one galaxy among many. It would not stand out. It would not dominate. It would simply be one more piece of the structure, unremarkable and ordinary in that context. But here's something that might surprise you about galaxy clusters. When you look at one, most of what you're seeing is not galaxies. The galaxies themselves, the bright collections of stars that seem like the main attraction, the objects your eye would naturally focus on, make up only a small fraction of the cluster's total ordinary matter. Maybe 10 to 15%. The vast majority of the normal matter in a galaxy cluster, roughly 85 to 90% of it, exists as an enormous cloud of hot gas that fills the space between the galaxies. This gas is called the intracluster medium, and understanding it is essential to understanding everything that comes next. Because the intracluster medium is not a passive backdrop. It's not just empty space with a few stray atoms floating around. It's one of the most extreme environments in the entire universe, and it plays a central role in the story of Phoenix A. The intracluster medium is superheated plasma. Gas so unbelievably hot that every atom in it has been stripped of its electrons. When you think of gas, you probably think of something gentle. The air around you, steam rising from a pot of water, maybe the wind on a breezy day. The intracluster medium is nothing like any of those things. The temperature of this plasma in the Phoenix cluster reaches tens of millions of degrees. For comparison, the surface of our sun is about 10,000 degrees Fahrenheit. The core of the sun, where nuclear fusion occurs, crushing hydrogen into helium under tremendous pressure, is about 27 million degrees Fahrenheit. The gas filling the space between galaxies in the Phoenix cluster is comparable in temperature to the interior of a star. Except, this isn't a compact ball of plasma like the sun. This is a vast ocean of it, extending for millions of light years in every direction, filling the entire cluster volume like an unimaginably hot fog. You can't see this gas with your eyes. Human eyes only detect visible light, but the intracluster medium radiates intensely at X-ray wavelengths. X-ray telescopes in space, orbiting above Earth's atmosphere, which blocks most X-rays from reaching the ground, can detect this radiation clearly. When NASA's Chandra X-ray Observatory turned its instruments toward the Phoenix cluster, it revealed one of the most luminous X-ray sources among all known galaxy clusters. The sheer amount of X-ray radiation pouring out of this cluster was extraordinary. It told astronomers that the gas was not only incredibly hot, but also remarkably dense by the standards of intergalactic space. And that combination, intense heat and relatively high density, creates a situation with profound consequences. Because dense, hot gas radiates energy efficiently. It glows, it pours out X-rays, and as it radiates all that energy into space, it loses thermal energy. It cools. But before we get to the cooling, you need to understand just how extreme the Phoenix cluster's gas really is compared to other galaxy clusters. Because not all clusters are created equal. Some have relatively modest cores where the gas is warm and thin. Others have dense, bright cores where the gas is packed more tightly and radiates more intensely. Astronomers classify these as cool core clusters, systems where the central gas density is high enough that the cooling time, the time it would take the gas to radiate away all its thermal energy, is shorter than the age of the universe. Many massive clusters have cool cores, but the Phoenix cluster's core is in a class by itself. The X-ray luminosity of the Phoenix cluster is among the highest of any galaxy cluster ever observed. When Chandra pointed its instruments at this system, the central region was blazing in X-rays, with an intensity that placed it at or near the top of every catalogue of known clusters. The luminosity of the hot gas in the Phoenix cluster's core exceeds that of most other cool core clusters by a wide margin. It's not just a bright cluster, it's one of the brightest cluster cores in the entire observable universe. This brightness is a direct consequence of density. X-ray emission from hot plasma scales with the square of the gas density. Double the density and the X-ray output doesn't just double, it quadruples. Triple the density and the output goes up by a factor of 9. The central regions of the Phoenix cluster have gas densities significantly higher than what you'd find in a typical massive cluster. The gas near the core is packed more tightly, the electrons are more numerous per unit volume, and the result is a furnace of X-ray emission that dwarfs most other systems. This matters enormously for everything that comes later in this story, because the density of the gas determines how hard it is to push aside. Think of it this way. Imagine trying to dig a hole in loose, dry sand versus trying to dig a hole in wet-packed clay. The same shovel, the same effort, produces a much larger hole in sand than in clay, because the clay resists displacement far more strongly. The intracluster medium of the Phoenix cluster is the cosmic equivalent of wet-packed clay. It's dense, it's pressurized, it pushes back. Any jet trying to inflate a cavity in this gas has to work harder, expend more energy, sustain more power for a longer time than it would in a less dense environment. The fact that the jets from Phoenix A have carved enormous cavities in this particular medium, rather than in some thin, tenuous gas filling a modest cluster, is what makes the energy requirements so staggering. You're not blowing bubbles in air, you're blowing bubbles in the densest, hottest, most resistant intergalactic gas the universe has to offer. This is where things get really interesting. In most galaxy clusters, there's a delicate balance at work. The hot gas in the cluster center radiates energy and slowly cools, but something pumps heat back into the gas, preventing it from cooling too rapidly. This is a critical process, and we'll explore exactly what provides that heat in detail later, because it turns out to be one of the most spectacular phenomena in astrophysics. But for now, what matters is this. In the Phoenix cluster, that balance is disrupted. The gas near the center of the cluster is cooling faster than in almost any other known cluster. The cooling rate is extraordinary. The intracluster medium near the core of the Phoenix cluster is losing energy at a pace that dwarfs what astronomers see in most other systems. And when gas in a galaxy cluster cools rapidly, it does what cold gas everywhere in the universe does. It collapses under gravity, it fragments into dense clouds, and those clouds form stars. The central galaxy in the Phoenix cluster is forming new stars at an almost unbelievable rate. In the Milky Way, we form roughly 1 to 2 new stars per year. That might sound modest, but it's actually a healthy, sustainable pace that has kept our galaxy going for billions of years. Our galaxy is not in a hurry. It makes its stars slowly, steadily, and has enough gas to keep doing this for a long time. The central galaxy in the Phoenix cluster is doing something completely different. It's forming stars at a rate of roughly 500 to 700 solar masses per year. Some initial estimates put the number even higher, closer to 750 solar masses per year. Think about what that means. In a single year, the central galaxy in the Phoenix cluster produces more new stars than the Milky Way creates in several centuries. In one human lifetime, this galaxy produces more stars than our galaxy creates in tens of thousands of years. It's one of the most prolific star-forming galaxies ever discovered anywhere in the observable universe. And it's doing this because of the enormous flood of cooling gas pouring inward from the surrounding intracluster medium. The gas cools, falls toward the center of the cluster, and the galaxy sitting at that center converts it into stars at a furious pace. This central galaxy is called Phoenix A. It's what astronomers refer to as a brightest cluster galaxy, sometimes shortened to BCG. The brightest cluster galaxy is the largest, most luminous galaxy sitting at the gravitational center of a galaxy cluster. Almost every massive cluster has one. These central galaxies grow enormously over cosmic time by consuming smaller galaxies that drift too close. They sit at the bottom of the cluster's gravitational well, the deepest point in the cluster's gravitational field, the place where everything slowly falls. And over billions of years, they grow. They accumulate mass. They eat. Phoenix A is a massive galaxy, far larger than the Milky Way, embedded in the densest region of the Phoenix cluster's hot gas, surrounded by more matter than most galaxies in the universe will ever encounter. If you could somehow see Phoenix A up close, it would be staggering. A vast elliptical structure packed with stars both ancient and newborn, glowing with the blue light of rapid star formation, wrapped in a halo of superheated plasma extending for millions of light years in every direction. The Milky Way, impressive as it is from our perspective on Earth, would look modest sitting next to Phoenix A. Our galaxy is a large spiral, genuinely one of the bigger galaxies in the universe, comfortably in the top 5% by most measures. But Phoenix A is in a different category entirely. It's a central, dominant galaxy in one of the most massive clusters ever discovered, and it has been growing for billions of years by swallowing everything that comes near it. But Phoenix A's size is not what makes it truly remarkable tonight. What makes Phoenix an extraordinary, what makes it the centerpiece of this entire story, is what sits at its very center. Because deep in the core of this massive galaxy, surrounded by billions of stars, immersed in a flood of inflowing gas, there is a black hole. And this is not just any black hole. This is one of the most massive black holes ever measured in the history of astronomy. The supermassive black hole at the center of Phoenix A has an estimated mass of roughly 100 billion times the mass of our sun. Let that number settle for a moment. 100 billion solar masses. Our sun is already enormous by any human standard. It has a diameter of about 864,000 miles. You could fit approximately 1.3 million Earths inside it. It contains 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, all of it together makes up only a tiny fraction of the solar system's mass. The sun dominates everything, and this black hole in Phoenix A has the mass of 100 billion of those suns, compressed into a single object so dense that not even light can escape its gravitational pull. To put this in perspective, let's compare it to some other famous black holes. The black hole at the center of our Milky Way, Sagittarius E star, has a mass of about 4 million times the mass of the Sun. That already sounds extraordinary. 4 million suns worth of mass is packed into a region smaller than our solar system. Sagittarius E star is a genuinely massive object by any standard. The black hole in M87, the giant galaxy at the center of the Virgo cluster, the one that was famously imaged by the Event Horizon Telescope collaboration in 2019, has a mass of about 6.5 billion solar masses. That's roughly 1,600 times more massive than Sagittarius A star. When that image was released, it captivated the entire world. People stared at the glowing ring of superheated gas surrounding a dark shadow and tried to comprehend a black hole with the mass of 6.5 billion suns. It was one of the most celebrated scientific images in history. The black hole in Phoenix A is estimated to be roughly 15 times more massive than M87's black hole. 15 times. If you took Sagittarius E-like star, the black hole at the center of our own galaxy, and you wanted to build the Phoenix a black hole out of copies of it, you would need roughly 25,000 of them. 25,000 copies of the supermassive black hole at the heart of the Milky Way, all combined into a single object. That is what sits at the center of Phoenix A. Now, estimating the mass of a black hole at this distance is not straightforward. You can't simply put it on a scale. Astronomers use indirect methods. They study the motions of stars and gas near the black hole. They measure the properties of the jets it produces and the enormous cavities those jets carve into the surrounding gas. They use scaling relationships between black hole mass and properties of the host galaxy that have been calibrated on closer, better studied systems. These methods involve significant uncertainties. The mass of the Phoenix A black hole could be somewhat higher or somewhat lower than 100 billion solar masses. But even accounting for generous error bars, even using the most conservative estimates, this black hole is among the most massive objects of its kind ever identified anywhere in the observable universe. It occupies a class that very few black holes enter, a category where the numbers become so extreme that comparisons to anything in everyday experience become essentially meaningless. And here's what matters most for our story tonight. This black hole is not dormant. It's not sitting quietly at the center of Phoenix A, passively warping space-time around it while the rest of the universe goes on undisturbed. It's active. It's feeding. Matter from the surrounding galaxy and from the cooling intracluster medium is falling toward it, spiraling inward, accelerating to tremendous speeds, heating up to extraordinary temperatures, and releasing staggering amounts of energy in the process. The Phoenix A black hole is what astronomers call an active galactic nucleus. It's an engine, one of the most powerful engines in the known universe, and it's running right now 5.7 billion light years from where you're sitting. When matter falls toward a supermassive black hole, it doesn't just drop straight in. Conservation of angular momentum, the same principle that keeps a figure skater spinning faster when they pull their arms in, prevents that. Instead, the infalling material spirals inward, flattening out, forming a rapidly rotating structure called an accretion disk. This disk is one of the most energetic environments in all of astrophysics. The gas in the inner regions of the accretion disk is compressed and heated by friction, magnetic forces, and gravitational energy being converted into thermal energy. Temperatures in the inner disk can reach billions of degrees. At these temperatures, the gas radiates enormous amounts of energy across the entire electromagnetic spectrum, from radio waves to infrared, to visible light, to ultraviolet to X-rays and gamma rays. A single active galactic nucleus, powered by one supermassive black hole feeding on infalling gas, can outshine the entire galaxy that hosts it. Hundreds of billions of stars and the tiny region around the black hole can produce more light than all of them combined. That's how much energy is released when matter falls into the deepest gravitational wells in the universe. But the accretion disk is only part of the story. Because some active galactic nuclei, including the one in Phoenix A, produce something even more dramatic. Something that will change how you think about scale in the cosmos. They produce jets. Relativistic jets. These are narrow, focused beams of matter and energy that shoot outward from the poles of the black hole, perpendicular to the accretion disk, at velocities that can reach significant fractions of the speed of light. The exact mechanism that launches these jets is still an active area of research, one of the major open questions in high-energy astrophysics. But the leading theoretical framework involves the interaction between the black hole's rapid spin, the accretion disk's magnetic fields, and the twisting of those fields by the rotation of space-time itself near the event horizon. The magnetic field lines become tightly wound, forming a funnel-like structure along the black hole's rotational axis. Matter and energy get channeled into this funnel and accelerated outward at extraordinary speed, forming a beam that can remain collimated and coherent across vast distances. These jets carry an almost inconceivable amount of energy. They're not just beams of light, they're streams of relativistic particles, primarily electrons and positrons, moving at close to the speed of light, guided by powerful magnetic fields, punching outward from the immediate vicinity of the black hole into the surrounding environment. In some systems, these jets extend for thousands of light years. In others, tens of thousands. In the most extreme cases, they reach hundreds of thousands of light years, or even more, far beyond the boundaries of the galaxy that hosts them, pushing out into intergalactic space. And in the case of Phoenix A, that surrounding environment is not an empty intergalactic void. It's the dense, hot, X-ray luminous intracluster medium of one of the most massive galaxy clusters in the observable universe. The jets from Phoenix A are slamming into one of the densest, hottest reservoirs of gas that exists between galaxies anywhere. And what happens when that collision occurs? When relativistic jets carrying the energy output of 100 billion solar mass black hole meet the superheated plasma filling a massive galaxy cluster is the central event of this entire story. Because the jets don't just dissipate, they don't fizzle out after a few thousand light years and surrender their energy quietly into the surrounding gas. They push, they shove, they carve out enormous cavities in the hot plasma, inflating vast bubbles of relativistic material that grow and grow and grow until they reach sizes that have nothing to do with galaxies anymore. These cavities, these bubbles blown by the jets of a single black hole, are the structures that make galaxies stop feeling like the biggest thing in the room. And their scale, when you actually measure it, will change how you think about size in the universe forever. But before we get to those measurements, we need to understand exactly how this works. How a black hole, an object whose event horizon might span a region not much larger than our solar system, can possibly create structures hundreds of thousands of light years across. We need to understand the physics of how a point source of energy, concentrated in a space smaller than you could cross in a single day at the speed of light, can inflate something larger than a galaxy. Because of that mechanism, that extraordinary transfer of energy from the smallest scales to the largest is one of the most remarkable processes in all of astrophysics. And it's happening right now, at this very moment, 5.7 billion light years away, in the heart of the Phoenix cluster, driven by one of the most massive black holes ever discovered, feeding on gas that has been raining down toward it for millions of years, converting that infall into energy so vast it reshapes the universe around it for hundreds of thousands of light years in every direction. The black hole at the center of Phoenix A is not just an object, it's an engine of simultaneous creation and destruction. And the structures it's building are about to change how you think about what large really means. To understand how a single black hole can build a structure larger than a galaxy, you need to understand one of the most violent and energetic processes in the universe. The process by which matter falling into a black hole gets converted into outgoing energy so powerful it can reshape the cosmos across hundreds of thousands of light years. This process is called active galactic nucleus feedback, and it begins with something deceptively simple: gravity pulling gas inward. Let's start at the beginning. Every massive galaxy has a supermassive black hole at its center. This isn't speculation. It's one of the most well-established observations in modern astrophysics. We've measured black holes in dozens of galaxies directly, using the motions of stars and gas orbiting near them, and the relationship between a galaxy's properties and the mass of its central black hole is so tight, so consistent, that astronomers are confident the connection is universal. Big galaxies have big black holes. Small galaxies have smaller ones. The black hole and its host galaxy grow together over cosmic time, linked by a relationship that we're still working to fully understand. Most of the time, these black holes are quiet. Sagittarius AY star, the 4 million solar mass black hole at the center of our own Milky Way, is essentially dormant right now. There's very little gas falling into it. It produces a faint trickle of radio emission, barely detectable even with our best instruments. If you didn't know it was there, you'd never notice. It's like a massive engine that's been turned off, sitting idle, waiting for fuel. Most supermassive black holes in the universe at this moment are in a similar state. They exist. They warp space-time around them. But they're not doing much. But when gas does fall towards a supermassive black hole in significant quantities, everything changes. The black hole wakes up. And when a supermassive black hole wakes up, it becomes one of the most luminous, most energetic objects in the entire observable universe. The key to understanding this is the accretion disk. When gas approaches a black hole, it almost never falls straight in. Gas in the real universe has angular momentum. It's moving, it's swirling, it has inherited motion from whatever larger structure it was part of, whether that's a galaxy, a gas cloud, or the intracluster medium raining inward in a massive galaxy cluster. Conservation of angular momentum, the same physical principle that makes an ice skater spin faster when pulling their arms inward, prevents this gas from simply plunging directly into the black hole. Instead, the gas spirals. It flattens out into a rotating disk structure, orbiting the black hole at tremendous speed, with material as smaller radii orbiting faster than material farther out. This differential rotation is where the magic happens. Gas at different distances from the black hole is moving at different speeds. This creates friction between adjacent layers of gas, and that friction generates heat. Enormous amounts of heat. The gas in the inner regions of the accretion disk, closest to the black hole where the gravitational field is strongest and the orbital speeds are fastest, gets compressed and heated to extraordinary temperatures. We're talking about tens of millions, hundreds of millions, sometimes billions of degrees. At these temperatures, the gas radiates ferociously across the entire electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. Every type of electromagnetic radiation is pouring out of this relatively tiny structure surrounding the black hole. Here's the remarkable thing about this process. It's one of the most efficient energy conversion mechanisms in all of physics. When gas falls toward a black hole and spirals through an accretion disk, somewhere between 6 and 42% of the mass energy of that gas gets converted into radiation before it crosses the event horizon. The exact efficiency depends on how fast the black hole is spinning. A non-spinning black hole converts roughly 6%. A rapidly spinning black hole, one spinning near its theoretical maximum, can convert up to roughly 42%. Compare that to nuclear fusion, the process that powers the sun and all the stars in the universe. Fusion converts only about 0.7% of mass into energy. That means accretion onto a black hole is roughly 10 to 60 times more efficient than the process that lights every star in every galaxy. A black hole accretion disk converting matter into energy is, pound for pound, the most powerful, sustained energy source the universe has ever produced. This is why active galactic nuclei are so luminous. A single supermassive black hole, feeding on infalling gas, can produce more light than the entire galaxy surrounding it. Hundreds of billions of stars, and the tiny region around the black hole, a region that might be no larger than our solar system, can outshine all of them combined. The first quasar ever identified, 3C273, discovered in 1963, initially baffled astronomers because it appeared star-like in photographs, but had a redshift indicating it was billions of light years away. Nothing at that distance should appear that bright unless it was producing an almost inconceivable amount of energy. It took years for the scientific community to accept that the power source was matter falling into a supermassive black hole. The idea seemed almost too extreme, but the evidence was overwhelming. Only gravitational energy, released through accretion onto a black hole, could explain the luminosities being observed. But luminosity, raw electromagnetic radiation streaming outward in every direction, is only half the story. Because some active galactic nuclei produce something even more dramatic than light. They produce jets. Relativistic jets are among the most extraordinary phenomena in the known universe. They are narrow, tightly focused beams of matter and energy that erupt from the immediate vicinity of the black hole, shooting outward along the black hole's rotational axis, perpendicular to the accretion disk, at speeds that can reach more than 99% of the speed of light. These jets carry enormous amounts of kinetic energy, magnetic energy, and the energy of the relativistic particles streaming within them. They're not gentle flows, they're cosmic blowtorches, focused and sustained, capable of punching through the gas surrounding the galaxy and extending outward for staggering distances. The mechanism that launches jets is one of the most studied and debated topics in astrophysics. The leading theoretical framework, developed over decades by physicists building on the work of Roger Blanford and Roman Znajek in 1977, involves the interplay between three things: the spin of the black hole, the magnetic field threading the accretion disk, and the warping of space-time near the event horizon. A spinning black hole doesn't just sit there passively curving space-time, it drags space-time around with it, a phenomenon called frame dragging predicted by Einstein's general theory of relativity. Near the event horizon of a rapidly spinning black hole, space itself is being twisted and pulled in the direction of the black hole's rotation. Magnetic field lines, which are anchored in the electrically conducting plasma of the accretion disk, get twisted by this frame-dragging effect. They wind up tighter and tighter, like a rubber band being twisted around a finger, building up enormous magnetic pressure. Eventually, this twisted magnetic structure forms a funnel-shaped channel along the black hole's rotational axis. Charged particles, mainly electrons and positrons, get caught in this funnel. The magnetic pressure and the electromagnetic forces accelerate them outward along the funnel axis at velocities approaching the speed of light. The result is a jet, a tightly collimated beam of relativistic plasma, guided by magnetic fields, powered ultimately by the rotational energy of the black hole itself and the gravitational energy of the infalling gas. The jet shoots outward from each pole of the black hole, so in most cases you get two jets, one from the North Pole and one from the South Pole, pointing in opposite directions. Each jet carries a significant fraction of the total energy being released by the accretion process. In some systems, the power carried by the jets exceeds the total luminosity of the accretion disk itself. The jets become the dominant channel through which the black hole releases energy into the universe. Now, let's think about what happens when one of these jets meets the surrounding environment, because this is where the story of Phoenix A truly becomes extraordinary. In some galaxies, the jets erupt into relatively empty space. The intergalactic medium outside galaxy clusters is thin, tenuous, almost a perfect vacuum by everyday standards. In those environments, jets can travel enormous distances with relatively little resistance. They just keep going, pushing outward, extending farther and farther from the host galaxy. Some radio galaxies have jets that extend for millions of light years, creating enormous lobes of radio-emitting plasma on either side of the central galaxy. These are already structures much larger than any single galaxy. But Phoenix A is not sitting in a void. Phoenix A sits at the center of one of the most massive galaxy clusters in the observable universe, and that means the jets from Phoenix A are erupting into one of the densest, hottest, most pressurized environments that exists between galaxies anywhere in the cosmos. The intracluster medium of the Phoenix cluster is not a gentle, thin gas. It's superheated plasma at tens of millions of degrees, dense enough to glow brilliantly in X-rays, extending for millions of light years in every direction around Phoenix A. This plasma has pressure, real, significant, thermal pressure that pushes back against anything trying to displace it. When the relativistic jets from Phoenix A's central black hole slam into this hot, pressurized intracluster medium, the collision is spectacular. The jets don't just punch clean through the gas and keep going forever. They can't. The surrounding medium is too dense, too pressurized. Instead, the jets decelerate. They slow down. They spread out. And as they spread, they inflate enormous bubbles in the surrounding gas, pushing the hot intracluster medium aside and creating vast cavities filled with relativistic plasma. Think of it this way. Imagine you have a container filled with a thick, heavy fluid. Now imagine you take a high-pressure hose and shove it into the fluid and turn it on. The water from the hose doesn't just pass through the fluid cleanly. It pushes the fluid outward, creating a cavity, a pocket of fast-moving water surrounded by the displaced heavy fluid. The faster and longer you run the hose, the bigger the cavity gets. The surrounding fluid is pushed farther and farther away. The cavity inflates. This is essentially what the jets from Phoenix A are doing to the intracluster medium. Except instead of a hose, The energy source is a 100 billion solar mass black hole. Instead of water, the jet material is relativistic plasma moving at nearly the speed of light. Instead of a container of fluid, the surrounding medium is a vast ocean of superheated gas, tens of millions of degrees hot, filling a galaxy cluster millions of light years across. And instead of taking a few seconds, this process has been going on for millions of years. The result is a pair of enormous cavities, one on each side of the central galaxy, inflated by the two opposing jets. These cavities are not empty in the traditional sense. They're filled with the relativistic plasma deposited by the jets. Plasma that emits radio waves as electrons spiral around magnetic field lines. This is called synchrotron radiation, and it's how radio telescopes can observe these structures. The cavities glow at radio wavelengths, revealing their shape, their size, and their energy content. But from the perspective of X-ray telescopes, the cavities appear as shadows, dark holes in the otherwise bright X-ray glow of the intracluster medium. The hot gas has been pushed aside, displaced by the jets, leaving a region where the X-ray emission is absent or suppressed. These X-ray cavities are one of the primary tools astronomers use to study the impact of jets on their surroundings. By measuring the size of the cavities and the pressure of the surrounding gas, you can estimate how much energy was required to inflate them. And those energy estimates are staggering. Here's why the cavities grow so large. The jets are not a brief event, they're sustained. The black hole at the center of Phoenix A has been feeding for a long time, possibly tens of millions of years, and during that entire period the jets have been continuously pumping energy into the surrounding gas. This isn't a single explosion that dissipates quickly. It's a steady, relentless injection of power, pouring into the intracluster medium year after year, millennium after millennium, pushing the cavities larger and larger, and the amount of energy involved is almost beyond comprehension. The mechanical power of the jets in systems like Phoenix A can reach 10 to the 45 to 10 to the 46 ergs per second. For context, the total luminosity of the Sun, all the light and heat it produces through nuclear fusion, is about 4 times 10 to the 33 ergs per second. A single jet from an active galactic nucleus in a system like Phoenix A can carry as much power as trillions of suns. The combined mechanical output of both jets, sustained over millions of years, injects a cumulative energy into the surrounding gas that rivals the total gravitational binding energy of the intracluster medium itself. In other words, the black hole is releasing enough energy to significantly affect the thermal state of an entire galaxy cluster, a structure containing thousands of galaxies. The physics of how the cavities maintain their structure is fascinating. You might wonder why they don't simply collapse. After all, the surrounding intracluster medium is hot and pressurized. It should want to rush back into the cavities and fill them. But the cavities are supported by the pressure of the relativistic plasma inside them. The magnetic fields and the fast-moving particles trapped within the cavities exert an outward pressure that balances the inward pressure of the surrounding thermal gas. As long as the jets keep feeding energy into the cavities, or as long as the internal pressure remains high enough, the cavities persist. Over time, the cavities do evolve. As they inflate, they become buoyant. The relativistic plasma inside them is much less dense than the surrounding hot thermal gas, just as a bubble of air is less dense than the water surrounding it. This buoyancy causes the cavities to rise, drifting outward from the cluster center like enormous bubbles floating upward through a thick liquid. As they rise, they can detach from the jets that created them, becoming ghost cavities, relics of past jet activity that float outward through the intracluster medium, slowly expanding and fading over hundreds of millions of years. In many galaxy clusters, astronomers have found multiple generations of cavities. A young pair still connected to the active jets, an older pair that has risen farther out, and sometimes even older ghost cavities at even greater distances from the center. Each pair represents a different episode of jet activity from the central black hole. Each pair records a period when the black hole was actively feeding and pumping energy into its surroundings. In the Phoenix cluster, the cavities currently visible are among the most energetic ever observed. Their enormous size, which we'll explore in precise detail shortly, tells us that the jets from the central black hole have been injecting a phenomenal amount of energy into the intracluster medium. The fact that these cavities exist in such a dense, pressurized environment makes their size even more extraordinary. It takes far more energy to inflate a cavity in a dense medium than in a thin one. Imagine trying to blow a bubble in water versus blowing a bubble in air. The water resists. It pushes back harder. You need more pressure, more sustained effort, to create a bubble of the same size. The intracluster medium of the Phoenix cluster is among the densest and hottest of any known cluster. Pushing it aside, carving out cavities hundreds of thousands of light years across, requires an almost unimaginable amount of energy, and yet that's exactly what's happening. The black hole at the center of Phoenix A is doing it right now. But there's something else happening inside these cavities that matters enormously. Something beyond just the raw displacement of gas. Because the energy deposited by the jets doesn't stay locked inside the cavity walls. It leaks outward. It spreads. It affects gas far beyond the immediate boundaries of the bubbles themselves. And the way it spreads tells us something profound about how the universe works on the largest scales. When the jets inflate a cavity, they don't just push the surrounding gas aside cleanly and neatly. The interaction is violent. The boundary between the relativistic plasma inside the cavity and the hot thermal gas outside it is turbulent and unstable. Fluid instabilities develop along this interface, the same kinds of instabilities you see when you pour cream into coffee and watch the swirling patterns form at the boundary between the two fluids. These instabilities cause mixing. Hot relativistic plasma from inside the cavity gets stirred into the cooler thermal gas surrounding it, transferring energy from the cavity into the broader intracluster medium. This turbulent mixing is one of the primary channels through which the energy from the jets gets distributed across the cluster volume. But turbulence isn't the only channel. The inflation of the cavities also generates sound waves. Real, physical pressure waves that propagate outward through the intracluster medium at the local speed of sound, which in gas this hot is roughly 1,000 kilometers per second. These aren't gentle vibrations. They're powerful acoustic disturbances generated by the pulsing, rhythmic activity of the jets as they push against the surrounding gas. The waves radiate outward from the cavities like ripples from a stone dropped into a pond, carrying energy far beyond the cavity boundaries, depositing the energy as heat in the gas as the waves are gradually absorbed. In the Perseus cluster, one of the closest and best studied galaxy clusters with active AGN cavities, Chandra X-ray observations revealed concentric ripples in the hot gas surrounding the central galaxy. These ripples are sound waves, pressure fronts propagating outward through the intracluster medium, generated by the pulsing activity of the central black hole's jets. The sound waves in the Perseus cluster correspond to a frequency roughly 57 octaves below middle C on a piano, far too low for any human ear to detect, but real nonetheless. Each oscillation of those sound waves takes roughly 10 million years to complete. A single wave cycle stretches across tens of thousands of light years from peak to peak. These are the longest, slowest, deepest sounds in the known universe. Pressure pulses so drawn out that entire civilizations could rise and fall between one compression and the next. Real pressure waves carrying real energy through real gas across hundreds of thousands of light years. The black hole is essentially humming, and the entire cluster atmosphere vibrates in response. In the Phoenix cluster, the energy transport is even more extreme. The cavities are larger. The surrounding gas is denser. The energy being injected is greater. The sound waves, the turbulent mixing, and the shock fronts driven by the expanding cavity walls, all of these are operating at a higher intensity, distributing energy across a larger volume and affecting more gas than in almost any other known system. The entire core of the Phoenix cluster, spanning hundreds of thousands of light years, is being stirred and heated and reshaped by the mechanical output of one black hole. And there's a question of timescale that makes all of this even more striking. How long has this been going on? How long have the jets been running to inflate cavities this large? Astronomers can estimate this by looking at the size of the cavities and the speed at which they're expanding into the surrounding gas. The expansion speed is governed by the balance between the internal pressure of the cavity and the external pressure of the intracluster medium. In the Phoenix cluster, the estimated age of the current cavity system is somewhere in the range of tens of millions of years. Perhaps 50 million. Perhaps 100 million. By human standards, that's an inconceivably long time. It's longer than the entire age of our species. But by astronomical standards, it's brief. The universe is 13.8 billion years old. The Phoenix cluster itself has existed for billions of years. The current episode of jet activity represents a tiny fraction of the cluster's history. A brief period during which the black hole has been actively reshaping its environment. And in that brief period, cosmically speaking, the jets have built something larger than a galaxy. A structure that took billions of years of gravitational accumulation to assemble. The Milky Way, with its hundreds of billions of stars gathered over the entire history of the cosmos, has been exceeded in size by a structure that took perhaps 50 million years to inflate. The jets work faster than gravity, they build bigger than gravity, and they do it from a single point. The cavities are not just impressive spectacles. They're not just record-breaking numbers for astronomers to catalogue. They serve a function, a critical function that affects the evolution of the entire galaxy cluster and, as we'll discover, the evolution of massive structures across the observable universe. That function, and what it means for our understanding of how the cosmos works, is the deepest implication of everything Phoenix A represents. But first, we need to confront the raw scale of these cavities head-on. We need to compare them directly to galaxies and feel, not just intellectually understand, but genuinely feel why structures this large force us to reconsider what big means in this universe. Because when you actually measure how large these cavities are, when you compare them to familiar objects like the Milky Way or Andromeda, your entire sense of cosmic scale shifts. Galaxies contain hundreds of billions of stars. They span tens of thousands or hundreds of thousands of light years. They are enormous, genuinely enormous, by any standard that makes sense from a human perspective. But a single black hole feeding on gas at the center of one galaxy can create structures that exceed the size of the galaxy that hosts it. A single point of energy release, concentrated in a region smaller than our solar system, can reshape the environment for distances that dwarf the galaxy it lives in. The engine is tiny, the exhaust is galactic. And in the case of Phoenix A, the exhaust is larger than a galaxy. This is the central insight. This is the physical shock at the heart of this story. Energy from a point source, a black hole, channeled through jets and sustained over millions of years, can inflate structures that surpass the scale of the largest gravitationally bound collections of stars in the universe. When you look at a galaxy and think, that's the biggest thing out there, you're wrong. The biggest visible structures in many galaxy clusters are not the galaxies themselves. They're the cavities carved by the central black hole's jets. Blown bubbles of relativistic plasma pushed outward through the hot gas, inflated by the most powerful, sustained energy source the universe has ever produced. And in the Phoenix cluster, those bubbles are immense. How immense? How do they compare to the Milky Way, to Andromeda, to the galaxies we think of as the largest individual objects in the sky? That comparison, when you lay it out in real numbers, is what will finally force you to reconsider what big means in this universe. Because the numbers are not subtle, they're not marginal, they don't represent a modest difference, a structure that's a little bigger than a galaxy. The cavities in the Phoenix cluster represent a scale jump that breaks your intuition about what a single object in space can be. The engine at the center of Phoenix A has been running for millions of years, pouring energy into the surrounding gas at a rate that rivals the luminosity of trillions of stars, fighting against a flood of cooling gas that would otherwise trigger the most extreme star formation event in the nearby universe. And the structures it has built, the cavities it has carved, and the volumes of displaced superheated plasma are waiting to be measured, waiting to be compared, waiting to show you why galaxies, for all their splendor, are not the last word on size in this cosmos. Now let's talk about what was actually measured, because so far I've described the mechanism. I've explained how jets work, how they inflate cavities, and why the environment inside the Phoenix cluster makes this process extraordinary. But none of that prepares you for the actual numbers. The actual dimensions of the structures that the black hole at the center of Phoenix A has produced. The cavities carved by the jets of Phoenix A span a combined extent of roughly 600,000 light years across. Let that number just sit there for a moment. 600,000 light years. That's the approximate scale of the full cavity system. The paired bubbles inflated on opposite sides of the central galaxy by the two opposing jets. Each individual cavity extends for several 100,000 light years from the center. Together they form a structure so vast that it dwarfs the galaxy that produced them. It dwarfs most galaxies in the observable universe. It's a structure built not by the slow gravitational accumulation of billions of stars over billions of years, but by the sustained energy output of a single point source at the center of one galaxy, running for perhaps 10 to 100 million years. Now, let me give you the comparisons that actually make this number meaningful, because 600,000 light years on its own is just a number. A big number, certainly, but numbers alone don't reshape your understanding. What reshapes your understanding is comparison. It's placing one thing next to another and feeling the difference. The Milky Way, our home galaxy, the structure that contains every star you have ever seen with your naked eye, every constellation that ancient humans used to navigate the oceans and tell stories around campfires, the galaxy that hosts our sun, our planet, and our entire civilization is roughly 100,000 light years across. That's already an enormous distance. Light, traveling at 300,000 kilometers per second, the fastest speed anything in the universe can achieve, needs 100,000 years to cross from one edge of the Milky Way to the other. If you had started your journey across the Milky Way at the speed of light when the last ice age was ending on Earth, when humans were still using stone tools and hunting woolly mammoths, you would not have arrived at the other side yet. You'd still be traveling. You'd still have thousands of years to go. That's how large the Milky Way is. The cavity system produced by Phoenix A's jets is 6 times larger than the entire Milky Way. 6 Milky Ways, laid end to end, lined up in a row. That's how wide this structure is. You could take our entire galaxy, this enormous spiral containing hundreds of billions of stars, and you could fit 6 of them across the span of the cavities inflated by one black hole at the center of one galaxy in one cluster. The Milky Way, the thing we call home, the structure that contains everything we have ever known or experienced, fits inside this cavity system the way a tennis ball fits inside a bathtub. It's not even close to filling it. It rattles around inside it. Now let's try another comparison. The Andromeda Galaxy, the largest galaxy in our local group, is about 220,000 light years across. Andromeda is a giant by any standard. It's larger than the Milky Way. It contains roughly 1 trillion stars. When it merges with our galaxy in about 4.5 billion years, the result will be one of the larger galaxies in the local universe. Andromeda is the biggest individual galaxy most people have ever heard of. It's the one you can see with your naked eye on a clear, dark night. A faint smudge of light in the constellation that shares its name. And it's impressive. Genuinely impressive. The cavity system of Phoenix A is roughly 3 times the diameter of the Andromeda Galaxy, 3 Andromedas across. The largest galaxy in our cosmic neighborhood, a galaxy containing 1 trillion stars, could be placed inside this cavity system nearly 3 times over. Andromeda, which seemed so massive, so dominant, so definitively large, suddenly feels modest. It's no longer the ceiling. It's not even close to the ceiling. It's just another galaxy, another collection of stars sitting well below the scale of the structures that a supermassive black hole can produce. Let me try to make this even more intuitive. If the Milky Way were the size of a standard dinner plate, roughly 10 inches across, the cavity system of Phoenix A would be about the size of a dining table. You'd set your plate down on the table, and the plate would occupy a small fraction of the surface. The table, enormous from the plate's perspective, would extend in every direction far beyond the edges of the plate. Your galaxy, everything you've ever known, would be a dish sitting on a table built by a single black hole. Or try this. Imagine you're standing in the center of the Milky Way, looking outward in the direction of one of Phoenix A's cavities. If you could somehow overlay that cavity onto our local region of space, it would extend from the center of the Milky Way outward, past the edges of our galaxy, past the void between galaxies, and a significant distance toward the Andromeda Galaxy itself. The cavity would eat up a large fraction of the empty space that separates us from our nearest, large galactic neighbor. A single bubble, inflated by jets from one black hole, would fill a substantial portion of the gap between two of the largest galaxies in the local group. This is what I mean when I say that galaxies stop feeling like the biggest thing in the room. We grow up learning that galaxies are the grand structures of the cosmos, collections of hundreds of billions of stars, spanning tens of thousands or hundreds of thousands of light years, gravitationally bound into magnificent spirals or massive ellipticals. And they are grand, they are magnificent. But the cavity system of Phoenix A is larger than any of them. Not slightly larger, not marginally larger, dramatically, overwhelmingly, almost absurdly larger. A structure produced not by the slow gravitational accumulation of matter over 13 billion years of cosmic history, but by the sustained output of a single engine running for a few tens of millions of years. A cosmic blink. And in that blink, the engine built something bigger than most galaxies will ever be. Now, let's talk about the energy required to do this, because size alone doesn't tell you the full story. You need to know how much energy it takes to push aside the intracluster medium of the Phoenix cluster, to carve out cavities this large in an environment this dense and this hot. Astronomers estimate the energy contained in these cavities by measuring two things: the volume of the cavities, which tells you how much gas was displaced, and the pressure of the surrounding intracluster medium, which tells you how hard it was to push that gas aside. The energy required is roughly the product of these two quantities. It's like calculating how much work it takes to inflate a balloon. You need to know how big the balloon is and how much pressure the surrounding air exerts on it. For the cavities in the Phoenix cluster, the total energy stored in them is estimated at roughly 10 to the 61 ergs. That's a 1 followed by 61 zeros. This number is so enormous that comparing it to anything in everyday experience is essentially futile. But let me try anyway, because the attempt itself reveals something about the scale of what's happening. The total energy output of our sun over its entire lifetime, from the moment it ignited hydrogen fusion roughly 4.5 billion years ago, to the moment it will exhaust its fuel roughly 5 billion years from now, is about 10 to the 51 ergs. The total lifetime energy output of our star, all the light and heat it has produced, or ever will produce over roughly 10 billion years, is 10 to the 51 ergs. The energy contained in the cavities of Phoenix A is about 10 billion times greater than the total lifetime energy output of our sun. 10 billion suns, each burning for 10 billion years, and you're still only at the energy scale of one cavity system around one galaxy in one cluster. This is one of the most energetic AGN outbursts ever recorded anywhere in the observable universe. The Phoenix cluster sits near the very top of the energy rankings for cavity systems. Very few objects anywhere in the cosmos have deposited this much mechanical energy into their surroundings. To truly appreciate how extreme this is, it helps to compare Phoenix A to other well-known systems where black holes have carved cavities in cluster gas. Because Phoenix A is not the only galaxy where this happens. AGN feedback is a common process. It occurs in most massive galaxy clusters, but the scale varies enormously from system to system, and Phoenix A sits at the extreme end. Consider the Perseus cluster, one of the nearest and best studied galaxy clusters. It lies roughly 240 million light years from Earth, much closer than the Phoenix cluster. The central galaxy in the Perseus cluster is Angiers C1275, also known as Perseus A. It hosts a supermassive black hole that's been actively producing jets and inflating cavities for a long time. The cavities in the Perseus cluster are well studied. They're visible as clear depressions in X-ray images, dark holes in the bright X-ray glow of the surrounding hot gas. The inner cavities, the youngest ones still connected to the active jets, are each roughly 60 to 70,000 light years across. That's about 2/3 the diameter of the Milky Way. Impressive by most standards, but far smaller than the cavities in the Phoenix cluster. The Perseus cluster also shows older, larger ghost cavities farther from the center, relics of past jet episodes that have risen buoyantly outward through the gas. These outer cavities are much larger, roughly 200,000 to 300,000 light years across. Substantial structures in their own right, yet still smaller than Phoenix A's full cavity system. The Perseus cluster demonstrates the same physical process, jets inflating bubbles in hot gas, but at a more modest energy scale. The cavities in the Perseus cluster contain roughly 10 to the 58 to 10 to the 59 ergs of energy. That's 100 to 1,000 times less energy than the cavities in the Phoenix cluster. Same process, vastly different scales. Then there's MS-0735, a galaxy cluster about 2.6 billion light-years away, that was once considered the gold standard for extreme AGN outbursts. The cavities in this system are enormous, with a combined extent exceeding 1 million light-years for the full pair, actually larger than Phoenix A's cavity system in raw linear size. The energy contained in those cavities was estimated at roughly 6 times 10 to the 61 ergs, higher than the Phoenix cluster depending on which measurements you use. MS-0735 showed astronomers for the first time just how energetic AGN outbursts could be. Its cavity system held energy equivalent to the total output of billions of suns over billions of years. When this system was first characterized in detail in the mid-2000s, it stunned the astrophysical community. Nothing on this energy scale had been clearly documented before. Phoenix A's cavities approached the energy scale of MS-0735, placing both near the very top of the known distribution. But what makes Phoenix A particularly striking is not just the size of the cavities, it's the context. It's where these cavities exist. MS-0735's cluster environment, while massive, has a somewhat lower central gas density than the Phoenix cluster. The intracluster medium in the Phoenix cluster is among the most luminous in X-rays of any known cluster, meaning the gas is exceptionally dense and hot near the center. Inflating cavities of this size in such a dense environment requires even more energy per unit volume than doing so in a less dense cluster. The fact that Phoenix A's black hole has managed to carve out enormous cavities in one of the densest, hottest intracluster environments known makes the energy output even more impressive in context. Now let me introduce another comparison that helps frame the scale from a different angle. There are structures in the universe produced by AGN jets that are even larger than Phoenix A's cavities in terms of total linear extent. Radio galaxies, galaxies whose jets have produced enormous lobes of radio-emitting plasma extending far into intergalactic space, can be truly colossal. The largest known radio galaxy is Alcide Neus, discovered in 2022. Alcide Neus has radio lobes stretching approximately 16 million light-years from end to end. That's about 160 times the diameter of the Milky Way. It's the largest known structure produced by a single galaxy anywhere in the observable universe. Compared to Alcide Neus, Phoenix A's cavity system of roughly 600,000 light-years is smaller in raw linear size significantly smaller. So why am I emphasizing Phoenix A rather than Alcyonius? Because raw size is not the only thing that matters. What makes Phoenix A's cavities so remarkable is the environment in which they exist and the energy density they represent. Alcyonius is a giant radio galaxy whose lobes extend into relatively low-density intergalactic space. The gas surrounding Alcyonius is thin and diffuse. There's very little resistance to the jets. They can expand outward almost freely, inflating enormous lobes with relatively modest energy investment per unit volume. It's like blowing a bubble in air. The air doesn't push back very hard, so the bubble can grow very large without requiring enormous pressure. The lobes of Alcyonius are vast, but they're also tenuous. They're spread thin across an enormous volume of nearly empty space. Phoenix A's cavities exist inside a galaxy cluster, inside a dense, hot, pressurized ocean of superheated plasma. The resistance to expansion is orders of magnitude higher. Every cubic light year of cavity volume that gets carved out requires pushing aside dense, hot gas that is pushing back hard. The energy density inside Phoenix A's cavities, the energy per unit volume, is far higher than in the lobes of a giant radio galaxy expanding into a void. Phoenix A's black hole isn't just producing a large structure, it's producing a large structure in one of the hardest places in the universe to produce a large structure. It's the difference between inflating a balloon in the open air and inflating a balloon underwater. The underwater balloon might be smaller in absolute size, but the pressure you had to exert to inflate it is vastly greater. And the fact that you managed to inflate it at all in that environment is far more impressive. This is why Phoenix A deserves its place in this story. Not because its cavity system is the absolute largest structure ever produced by a black hole. It isn't. But because its cavity system represents one of the most energetic, most forceful interactions between a supermassive black hole and its environment ever recorded. The sheer amount of work required to push aside the Phoenix cluster's intra-cluster medium, to carve out hundreds of thousands of light years, wide bubbles in gas that hot and that dense, places Phoenix A at the extreme end of what AGN feedback can accomplish. And it still makes Galaxies look small, even without being the single largest jet-inflated structure ever measured. Phoenix A's cavities are 6 times the diameter of the Milky Way. They dwarf Andromeda. They exceed the size of every galaxy in our local group. They exceed the size of most galaxies anywhere in the observable universe. The structure created by one black hole in one galaxy over a few tens of millions of years is larger than the gravitationally bound stellar systems that took the entire age of the universe to assemble. Let me try one more comparison to drive this home. Let's think about the local group, our cosmic neighborhood of roughly 50 galaxies. The local group spans about 10 million light years across. It includes the Milky Way, Andromeda, Triangulum, and dozens of smaller dwarf galaxies. It's everything we consider our immediate galactic neighborhood. Phoenix A's cavity system, at roughly 600,000 light years across, is about 6% of the diameter of the entire local group. A structure produced by one black hole in one distant galaxy is a measurable fraction of the width of our entire galactic neighborhood. It's not a rounding error. It's not a speck inside the local group. It's a significant chunk of it. Now, imagine what it would look like if you could see Phoenix A's cavities directly. If you could somehow render them visible to the human eye and view them from a distance where their full extent was apparent, you'd see a galaxy, Phoenix A itself, sitting at the center, a massive elliptical galaxy, far larger than the Milky Way, glowing with the blue light of rapid star formation and the fainter red and orange glow of its older stellar populations. And extending from this galaxy, reaching outward in opposite directions, two enormous lobes of diffuse emission, each one stretching for hundreds of thousands of light years, vastly exceeding the boundaries of the galaxy that spawned them. The galaxy itself would look like a bright core sitting inside a much larger cocoon. The cocoon would dwarf the galaxy the way a cloud dwarfs the raindrop, at its center. The thing you'd notice first, the thing that would dominate the view, wouldn't be the galaxy. It would be the cavities. The galaxy would be a detail inside a much larger structure. What's remarkable is that we can actually see these cavities, not with our eyes, obviously. Human eyes detect only visible light, and these structures don't emit much in the visible spectrum. But with the right instruments, the cavities reveal themselves clearly, and understanding how astronomers observe them helps you appreciate just how real and how physical these structures are. In X-ray images, taken by space telescopes like Chandra, the intracluster medium of the Phoenix cluster appears as a bright, glowing fog of emission. The hot gas fills the cluster volume, radiating X-rays in proportion to its density and temperature. Where the gas is densest, near the center of the cluster surrounding Phoenix A, the X-ray glow is most intense. The image looks like a luminous cloud with a bright core, gradually fading toward the edges as the gas becomes thinner and cooler at greater distances. But within that bright glow, there are shadows, dark regions where the X-ray emission drops significantly, places where the glowing gas should be, based on the smooth distribution you'd expect from gravity alone, but isn't. These dark patches are the cavities. They're voids in the X-ray emission, regions where the hot thermal gas has been physically pushed aside, displaced by the relativistic plasma injected by the jets. The gas isn't gone from the universe, it's been shoved outward, piled up around the edges of the cavities like soil pushed to the rim of a crater. But inside the cavity boundaries, the thermal gas is largely absent, and so the X-ray emission drops, leaving a dark depression against the bright background. Now switch to radio wavelengths. Radio telescopes see something completely different when they look at the same region. Where the X-ray images show dark shadows, the radio images show bright lobes, glowing structures filled with radio emission produced by the relativistic electrons spiraling through the magnetic fields trapped inside the cavities. The same volumes that appear dark in X-rays appear bright in radio. The two views are complementary. They're showing you the same physical structures from two different perspectives. The X-ray view shows you where the hot gas was pushed away. The radio view shows you what replaced it. Together, they paint a complete picture of what the jets have done to their environment. When you overlay these two sets of observations, aligning the X-ray shadows with the radio lobes, the match is striking. The radio emission fills the X-ray depressions almost perfectly. The cavities aren't theoretical constructs or model predictions. They're directly observed structures, visible in multiple wavelengths, confirmed independently by completely different types of telescopes, using completely different detection methods. They are as real as any other object in astronomy, as real as a star, as real as a galaxy, as real as anything you can point a telescope at and see. And when you look at these overlaid images, the scale becomes visceral in a way that numbers alone can't achieve. You see Phoenix A sitting at the center, a bright, compact source, and extending outward from it, filling the image, dominating the frame, two enormous lobes stretching in opposite directions, each one vastly larger than the central galaxy itself. The galaxy is a bright dot at the core of a structure that extends far beyond its boundaries in every direction. The cavities don't just exceed the galaxy in size, they overwhelm it visually. The cavities, not the galaxy, become the subject of the image. This visual impression captures the central paradox of what Phoenix A represents. We think of galaxies as the dominant structures on these scales. When you imagine the universe, you imagine galaxies, spirals and ellipticals drifting through the void. But in the Phoenix cluster, the dominant structures on these scales are not galaxies. They're the cavities. They're the bubbles blown by the central black hole. The galaxy is still there, still real, still containing billions of stars, but it's been eclipsed in scale by something it created. The child has outgrown the parent. And this isn't unique to the Phoenix cluster. Cavity systems comparable in size to or larger than their host galaxies have been observed in numerous galaxy clusters. The Perseus cluster has cavities that are significant fractions of the central galaxy's diameter. MS0735 has cavities comparable to Phoenix A's in size. The Hydra A cluster has multiple generations of cavities extending outward for hundreds of thousands of light years. Hercules A has spectacular jets producing enormous radio lobes. In cluster after cluster, wherever astronomers look with X-ray and radio telescopes, they find the same story. Central black holes inflating structures that approach or exceed the scale of galaxies. What makes Phoenix A stand out even in this company is the combination of all factors at once. An exceptionally massive black hole, one of the most massive ever measured, is sitting in an exceptionally massive galaxy, at the center of an exceptionally massive galaxy cluster, surrounded by an exceptionally dense and hot intracluster medium, producing cavities of exceptional size that contain exceptional amounts of energy, while simultaneously failing to fully suppress an exceptional rate of star formation. Every aspect of this system is extreme. Every number associated with it sits near the top of its respective distribution. Phoenix A is not just one impressive thing. It's a convergence of impressive things, each reinforcing the others, creating a system where the true scale of what a black hole can do is on full display. The black hole is 100 billion solar masses. The cluster mass is roughly 2.5 quadrillion solar masses. The star formation rate is 500 to 700 solar masses per year. The cavity energy is roughly 10 to the 61 ergs. The cavity extent is roughly 600,000 light years. Every one of these numbers is extraordinary individually. Together, they paint a picture of one of the most extreme astrophysical environments in the known universe. And at the center of it all is a single point: a black hole. An object whose event horizon, the boundary beyond which nothing can escape, spans a region comparable in size to our solar system. A region you could cross at the speed of light in roughly 3 weeks. From this tiny region, this pinprick in the fabric of space-time, enough energy has poured outward to reshape the cosmos for 600,000 light years in every direction. The ratio between the size of the engine and the size of its effect is staggering. The cavity system is roughly 10 million times larger than the event horizon that produced it. That's the same ratio as a single bacterium compared to a blue whale. The engine is unimaginably small compared to the structures it creates. And yet, the connection between them is direct, physical, measurable, and real. Energy flows from the accretion disk near the event horizon and gets channeled into jets by the twisted magnetic fields near the spinning black hole. And those jets punch outward for hundreds of thousands of light years, inflating cavities that make galaxies look like modest objects. This is why Phoenix A changes how you think about size in the universe. It's not that galaxies are small, they're not. The Milky Way is genuinely enormous, larger than 95% of all galaxies in the observable universe. Andromeda is even larger. These are grand, magnificent structures, the products of billions of years of cosmic evolution. But they're not the ceiling. They're not the largest things that exist on these scales. The largest structures in many massive galaxy clusters are not the galaxies themselves. They're the cavities, the lobes, the bubbles of relativistic plasma inflated by the jets of supermassive black holes. These structures exceed galactic scales routinely, and in the most extreme cases, like Phoenix A, they exceed galactic scales dramatically. The title of this episode asks why Phoenix A makes galaxies look small. Now, you know the answer. It's not that galaxies have somehow shrunk. It's that the structures produced by one black hole at the center of one galaxy have grown to a scale that surpasses what galaxies represent. When you stand next to something 6 times larger than the Milky Way stops feeling like the biggest thing around. Your sense of scale recalibrates, the ceiling lifts, and you realize that in this universe, the structures built by energy can exceed the structures built by gravity. 100 billion solar masses of concentrated gravitational collapse, focused into a single point, channeled through jets sustained over millions of years, can produce something that makes 100 billion freely orbiting stars spread across 100,000 light years look compact by comparison. Galaxies are not the last word on scale. Phoenix A proved that. And the implications of that proof for how we understand galaxy evolution, star formation, and the large-scale structure of the cosmos are profound. Because the cavities are not just impressive spectacles. They're not just record-breaking numbers for astrophysicists to catalogue and admire. They're functional. They serve a purpose. They play a critical role in regulating the behavior of the entire galaxy cluster. Without them, the Phoenix cluster would be a fundamentally different place. The central galaxy would be forming stars at a rate even more extreme than what we observe. The intracluster medium would be collapsing inward. The entire thermal state of the cluster core would be different. The cavities are not decorations. They're the visible evidence of a process that shapes how matter behaves across millions of light years. And understanding that process, understanding what the cavities tell us about the relationship between black holes and the universe around them, is where this story reaches its deepest implications. So we've established the scale, we've measured the cavities, we've compared them to galaxies and watched galaxies shrink. But now we need to ask the deeper question. The question that transforms Phoenix A from a spectacular curiosity into something that matters for the entire universe. Why do these cavities exist? Not just mechanically, not just in terms of jets and accretion disks and magnetic fields, but functionally. What role do they play? What would happen if they weren't there? Because the cavities carved by Phoenix A's jets are not just enormous structures floating passively in the intracluster medium. They're doing something. They're actively changing how the gas around them behaves. They're influencing whether that gas cools or stays hot, whether it forms stars or remains diffuse, whether the central galaxy grows or stays roughly the same size. The cavities are the visible fingerprints of a process that reaches across the entire cluster. A process that governs the evolution of the most massive gravitationally bound structures in the cosmos. And that process, AGN feedback, turns out to be one of the most important mechanisms in all of astrophysics. Let me explain why by describing what would happen without it. Imagine you could somehow turn off the black hole at the center of Phoenix A, shut down the jets, stop the accretion, remove the energy source entirely. What would happen to the Phoenix cluster? The answer is a catastrophe. Not instantly, not in human terms, but rapidly by astronomical standards. The intracluster medium near the center of the Phoenix cluster is radiating X-rays at an extraordinary rate. It's losing thermal energy constantly, pouring out radiation in every direction. Without the jets pumping energy back into this gas, there's nothing to replace the energy being lost. The gas near the center of the cluster would cool, not slowly, not gradually over billions of years, but relatively quickly, over tens of millions of years. As the gas cooled, it would lose pressure support. Hot gas exerts outward thermal pressure that supports it against the inward pull of gravity. Cool gas exerts less pressure. With less pressure, the gas falls inward, pulled toward the center of the cluster by the combined gravity of all the dark matter, all the galaxies, and all the other gas surrounding it. This infall would be enormous. The amount of gas cooling and flowing inward would be measured in thousands of solar masses per year. That's not a trickle, that's a flood. An avalanche of gas pouring into the central regions of the cluster, piling up on Phoenix A, burying it under a deluge of raw material. And when that much cold, dense gas accumulates in one place, it does what cold, dense gas always does in the universe. It fragments under its own gravity, collapses into knots and filaments, and those knots ignite into new stars. Star formation in the central galaxy would explode to rates of 1,000, 2,000, maybe several thousand solar masses per year. The galaxy would be manufacturing stars at a pace that dwarfs anything seen in normal galaxies, cranking out new stellar systems faster than almost any galaxy in the history of the universe. This scenario is called a cooling catastrophe, or sometimes a cooling flow, and for decades it was one of the biggest unsolved puzzles in the study of galaxy clusters. Astronomers could measure the properties of the hot gas in cluster cores. They could calculate how fast it was radiating energy, and when they ran the numbers, the cooling rates predicted that enormous amounts of cold gas should be accumulating at the centers of these clusters. Hundreds or thousands of solar masses per year of gas should be cooling, collapsing, and forming stars. The central galaxies in these clusters should be among the most actively star-forming galaxies in the universe, but they weren't. When astronomers actually looked at the central galaxies in most massive clusters, they found something puzzling. The star formation rates were much lower than the cooling models predicted. Sometimes 10 times lower, sometimes 100 times lower. The gas was clearly hot and clearly radiating energy. The cooling should have been happening. But something was preventing most of the gas from actually cooling all the way down to the temperatures needed to form stars. Something was intercepting the process, heating the gas back up, keeping it in a warm state where it couldn't collapse into stars. This puzzle persisted for more than 20 years. Astronomers called it the cooling flow problem, and it was one of the most stubborn, unresolved questions in extragalactic astrophysics. Theoretical models predicted massive cooling flows. Observations showed that those flows were largely absent. Something was wrong with the models, or something was happening in the clusters that the models weren't accounting for. The answer, when it finally came, was the jets. The supermassive black holes at the centers of these clusters were heating the gas. Not through radiation, not by shining light on the gas, but mechanically, through the physical work done by the jets as they inflated cavities in the intracluster medium. The jets were pushing gas aside, creating bubbles that rose buoyantly outward through the cluster atmosphere. As these bubbles rose, they stirred the gas. They generated turbulence. They created sound waves and shock waves that propagated outward through the intracluster medium, depositing energy as they traveled. The hot gas wasn't cooling unimpeded because the central black hole was constantly reheating it, fighting against the cooling, maintaining the gas at temperatures where it couldn't collapse efficiently into stars. This was the solution to the cooling flow problem, AGN feedback. The black hole acts as a thermostat. When the gas cools too much, more gas falls inward toward the black hole. The black hole gets more fuel. The jets become more powerful. The more powerful jets inject more energy into the gas, heating it back up. The gas stops cooling, less gas falls inward. The black hole gets less fuel. The jets weaken. Without the jets heating the gas starts cooling again. More gas falls inward. The cycle repeats. It's a self-regulating feedback loop that maintains a rough equilibrium between cooling and heating over billions of years. The evidence for this process is now overwhelming. It's been observed in dozens of galaxy clusters using X-ray telescopes. Nearly every massive cluster with a bright, dense, rapidly cooling core shows cavities in its X-ray emission. Dark holes where the jets have pushed the gas aside. When astronomers measure the energy contained in these cavities and compare it to the rate at which the surrounding gas is radiating X-rays, the numbers balance. The mechanical energy being injected by the jets is roughly equal to the energy being lost through X-ray radiation. The thermostat is working, not perfectly, not with complete precision in every system, but well enough to prevent the cooling catastrophe that would otherwise transform these clusters beyond recognition. And this is where Phoenix A becomes especially important, because the Phoenix cluster is one of the rare systems where the thermostat appears to be losing the battle, at least temporarily. The cooling rate in the Phoenix cluster is among the highest ever measured. The gas near the center is radiating X-rays so intensely that the energy loss is enormous, far higher than in most other clusters. The cavities are there. The jets are running. The black hole is doing everything it can to heat the gas. But the cooling is so extreme that the jets can't fully compensate. Gas is still cooling, still falling inward, still forming stars at 500 to 700 solar masses per year. This makes the Phoenix cluster one of the most valuable laboratories in all of astrophysics. It's a system where we can watch the feedback process in real time, operating near its limits. In most other clusters, the feedback has established a comfortable equilibrium. The jets have won. The cooling has been suppressed. The central galaxies are forming stars at modest rates, maybe a few solar masses per year. Everything is balanced and stable. There's not much drama. The Phoenix cluster is different. The Phoenix cluster is dramatic. It's a system caught in a moment of intense struggle. The black hole is producing some of the most energetic jets ever observed, inflating cavities containing roughly 10 to the 61 ergs of energy, and yet the cooling flow is still winning. Stars are forming at hundreds of times the Milky Way's rate. The gas is still pouring inward despite the enormous energy being pumped back into it. This tension, this near failure of the feedback mechanism, teaches us something profound about the limits of what black holes can do. It tells us that even the most powerful engines in the universe can be overwhelmed if the environment is extreme enough. There's another possibility that makes the Phoenix cluster even more fascinating. It might be in a transitional state. The current burst of extreme cooling and star formation might be temporary. A brief episode in the cluster's history where the balance tipped in favor of cooling. Perhaps the black hole's jets were weaker in the recent past, or perhaps there was a period when the accretion rate dropped, reducing the jet power. During that lull, the gas cooled rapidly, triggering the current starburst. Now the black hole is responding. The inflowing gas is feeding the black hole at a tremendous rate, powering the enormous jets we observe today. The cavities are inflating, the energy is being injected, and eventually, perhaps in another 10 or 50 million years, the jets might catch up. They might finally reheat the gas enough to shut down the cooling flow and return the cluster to a state of equilibrium. If this interpretation is correct, we're seeing the Phoenix cluster during a rare, brief, and extraordinary moment in its history. A moment when the thermostat was overwhelmed, but is now fighting back. This cycle, this oscillation between cooling and heating, between star formation and jet-driven suppression, is not unique to the Phoenix cluster. Astronomers believe it happens in many clusters over cosmic time. The feedback loop isn't a smooth, continuous process. It's episodic. It comes in bursts. The black hole turns on, inflates cavities, heats the gas, and then quiets down. The gas cools again. The black hole turns back on. Each cycle might last tens of millions of years. Over the lifetime of a galaxy cluster, which spans billions of years, there might be hundreds of these cycles. Each one leaves behind a pair of cavities that rise buoyantly outward through the gas, eventually fading into ghost cavities at large distances from the center. The cluster atmosphere is layered with the relics of past feedback cycles, each one a record of a time when the black hole fought against the cooling gas and won, at least temporarily. Now let's zoom out even further. Because AGN feedback doesn't just matter for the Phoenix cluster, it matters for the entire universe. Without AGN feedback, the universe would look fundamentally different. Galaxy clusters would have enormous, runaway cooling flows at their centers. The central galaxies in these clusters would be vastly more massive than they actually are, bloated with trillions of stars formed from all the gas that should have cooled, but was prevented from doing so by the jets. The relationship between galaxy size and black hole mass that we observe today, a tight correlation that holds across many orders of magnitude, wouldn't exist in the same form. The entire population of massive galaxies would be different. Computer simulations of the universe's evolution confirm this. When cosmologists run simulations of how the universe evolves from the Big Bang to the present day, they find that simulations without AGN feedback produce galaxies that are far too massive, too bright, and too blue. They form too many stars. They don't match what we actually observe. Only when AGN feedback is included. Only when the simulations account for energy injection from central black holes do the simulated galaxies match the real ones. AGN feedback is not optional in our models of the universe. It's essential. Without it, the models fail. The simulated universe doesn't look like the real universe. This means that supermassive black holes are not just exotic curiosities sitting at the centers of galaxies, they're architects, they're regulators, they're participants in the evolution of the largest structures in the cosmos. A black hole that weighs less than 1% of its host galaxy's total mass can determine how much that galaxy grows, how many stars it forms, and how the gas in the surrounding cluster behaves for millions of light years in every direction. The tail wags the dog. The tiny engine at the center controls the enormous machine that surrounds it. Phoenix A is the most vivid example of this principle in action. A black hole with a mass of roughly 100 billion suns, concentrated in a region comparable in size to our solar system, is reshaping the environment across 600,000 light years. It's influencing whether gas cools or stays hot across a volume larger than any galaxy. It's determining the star formation rate of the central galaxy. It's affecting the thermal state of the intracluster medium far beyond the galaxy's boundaries. A single point in space, smaller than a grain of sand compared to the structure it influences, is governing the behavior of one of the most massive objects in the observable universe. There's something almost paradoxical about this. We think of black holes as objects that consume, that swallow, that destroy, and they do consume and swallow and destroy. Anything that crosses the event horizon is gone. No light, no matter, no information escapes. Black holes are the ultimate endpoints of gravitational collapse, regions where gravity has won completely and nothing can resist it. But the process of consumption itself, the process of matter falling towards the black hole, generates more outgoing energy than any other process in the universe. The most destructive objects in the cosmos are also the most creative. They destroy what falls into them, but in doing so, they release energy that builds structures larger than galaxies. They consume, and in consuming, they construct. Phoenix A embodies this paradox perfectly. The black hole at its center is consuming gas at a tremendous rate. That gas is gone. It will never form stars, never become planets, never become anything other than part of the black hole's mass, locked behind the event horizon forever. But before that gas vanished, in the last moments before it crossed the point of no return, it released enough energy to reshape the cosmos across hundreds of thousands of light years. It powered jets that inflated cavities larger than the Milky Way. It heated gas that would otherwise have formed thousands of new stars every year. It influenced the evolution of the entire galaxy cluster for billions of years to come. The destruction of a relatively small amount of matter fueled the construction of one of the largest structures in the known universe. This brings us back to the question of scale, the question that this entire story has been building toward. What does big actually mean in this universe? When you started listening tonight, you probably had an intuitive sense of what the biggest things are. Galaxies, massive collections of hundreds of billions of stars, spanning tens of thousands or hundreds of thousands of light years, shaped by gravity over billions of years of cosmic history. Galaxies are the building blocks of the universe's large-scale structure. They're the units we think in when we imagine the cosmos. We talk about the Milky Way, about Andromeda, about distant spirals and ellipticals seen through telescopes. Galaxies are the protagonists of the cosmic story. But Phoenix A shows us that galaxies are not the end of the story. They're not the ceiling of scale. A single black hole feeding on gas at the center of one galaxy can produce structures that surpass galaxies in size. The cavities in the Phoenix cluster are 6 times the diameter of the Milky Way. They contain more energy than our sun will produce in its entire lifetime, multiplied by 10 billion. They influence the behavior of gas across a volume far larger than any galaxy. They are structures that exist on a scale where galaxies stop being the dominant reference point. And this isn't a freak occurrence. It's not a one-time anomaly. AGN feedback operates in galaxy clusters across the entire observable universe. Wherever there's a massive cluster with a hot, dense core and a central, supermassive black hole, you'll find evidence of jets and cavities. The scale varies. Some cavities are modest, a few tens of thousands of light years across. Others are enormous, hundreds of thousands of light years, rivaling or exceeding the sizes of the galaxies that produced them. But the phenomenon is universal. It's happening right now, at this moment, in thousands of galaxy clusters across the cosmos. Black holes are building structures larger than galaxies everywhere you look, as long as you look with the right instruments. This changes how you should think about the universe, not as a collection of galaxies floating passively in the void, but as a dynamic, interconnected system where the smallest and densest objects, black holes, interact with the largest and most diffuse objects, galaxy clusters, through feedback processes that span millions of light years. The universe is not a static backdrop. It's a machine. A vast self-regulating machine where energy flows from the smallest scales to the largest and back again, where gravity pulls matter inward and the energy released by that infall pushes matter outward, where destruction and creation are two sides of the same process. Phoenix A sits at the extreme end of this machine. It's one of the loudest, most energetic, most dramatic examples of AGN feedback in the known universe, but it's not fundamentally different from what's happening in quieter clusters closer to home. The Perseus cluster has its own cavities. The Virgo cluster has its own central black hole in M87, one that's been imaged directly. The Centaurus cluster, the Hydra cluster, Able 2597, cluster after cluster after cluster, they all show the same signs. Jets, cavities, feedback, regulation, black holes, building structures that transcend the galaxies they inhabit. Let me leave you with this perspective. You are sitting on a small rocky planet orbiting an ordinary star in a spiral galaxy 100,000 light years across. That galaxy is genuine in its enormity. It contains somewhere between 200 billion and 400 billion stars. Every point of light you see when you look up at the night sky belongs to it. Every constellation, every familiar pattern, every star that ancient humans used to navigate and tell stories and wonder about the nature of existence, all of it is part of the Milky Way. And the Milky Way is larger than 95% of all galaxies in the observable universe. It's not a small galaxy. It's one of the big ones. And yet, 5.7 billion light years from where you're sitting, a single black hole at the center of a single galaxy has produced a structure 6 times wider than our entire galaxy. A structure inflated by jets, sustained by accretion, carved into the superheated gas of a galaxy cluster that makes our local group look like a quiet village on the outskirts of a vast city. That structure is not made of stars. It's not held together by gravity. It's a bubble of relativistic plasma, pushed into existence by the most powerful engine the universe has ever produced, maintained by a feedback loop that has been running for millions of years and will continue running for millions more. This structure makes galaxies look small, not because galaxies have somehow diminished, not because they're less impressive than we thought, but because the energy released by a supermassive black hole, channeled through relativistic jets, sustained over cosmic timescales, can build things that exceed the scale of galaxies entirely. The ceiling we thought existed wasn't a ceiling at all. It was just another floor. The universe is bigger than galaxies, not just in the trivial sense that the universe contains many galaxies, but in the deeper sense that the universe contains individual structures produced by individual objects that surpass galaxies in scale. Phoenix A proved this. Its cavities are the evidence, and once you've seen that evidence, once you've understood what one black hole can do when it feeds in the right environment for long enough, you never look at galaxies the same way again. Galaxies are magnificent. They are the cathedrals of the cosmos, built by gravity over billions of years, containing the light of hundreds of billions of suns. But even cathedrals have a ceiling. And tonight, we found what's above it. A structure 600,000 light years across, inflated by the jets of one black hole, larger than the galaxy that birthed it, larger than our galaxy, larger than any galaxy in our cosmic neighborhood. A reminder that in this universe, energy can outbuild gravity, that a point source can reshape a volume, that destruction can produce creation, and that the true scale of the cosmos is always larger than you think. So the next time you look up at the night sky and see that faint band of light stretching overhead, the Milky Way, our home, one of the genuinely large galaxies in existence, remember what you learned tonight. Remember that somewhere out there, 5.7 billion light years away, a single point of concentrated gravitational collapse has produced a structure that would swallow our galaxy 6 times over. Remember that galaxies, for all their grandeur, are not the largest things this universe can make. And remember that the cosmos, as vast as it already seems, is always capable of surprising you with something bigger. That's the true scale of Phoenix A, and that's why it makes galaxies look small. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. Sleep well tonight, knowing that the universe is even more extraordinary than you imagined. And remember, every time you look up at the stars, you're looking at one galaxy among trillions. A galaxy that is genuinely large and genuinely beautiful, but that sits in a universe where even galaxies are not the last word on scale. Good night, and may you never look at the sky the same way again.